Hello and welcome to section 11.1, Parametrizations of Plane Curves. We just finished sequences and series, so we're going to move on to calculus in other coordinate systems and calculus with parametrized curves. We're going to start with the parametrized curves, and in order to talk about calculus with parametrized curves, we need to talk about what is a parametrization. So consider the following path. We could go wee. We have this path, and the arrows are indicating the direction that a particle would be moving if it traveled along this path. So the first question that you would ask, or that I would ask, is can you represent this path as a function? And no, you cannot. This cannot represent a single function. And that's because it fails the vertical line test. We could drop a line right here, vertical line, and it intersects at 2 points. So this is not a function. But let's say we wanted to, do some calculus on this because you have a particle that's traveling along this curve, and you want to see, well, how fast is it moving along this curve or something. So how do we go about doing that? Well, we can sometimes, can't always do this, describe such a path using a pair of equations. So we would use the equation, you'd find an equation for the x value as a function of time, and you'd find a function for the y value as a function of time. Not only will this give you an equation for the curve, but this also tells you the location of a particle at a given time. So you have the coordinate xy would equal the coordinate f of t, g of t. So if you wanted to figure out where the particle is after 10 seconds, you would just plug in 10 for t, assuming your time was measured in seconds. And also, because we can talk about where the particle is at a certain time, we can talk about the direction of the path, which is why we drew the arrows. I'm saying that the particle started here and then moved along the path in this direction and then ended here. So some definitions / terminology for dealing with parametrized curves. If x and y are given as functions, these functions be what I have above, x equal f of t, and y equal g of t. Let's underline that. And assume this is true over an interval I of t values. Then, the set of points x, y, which we could write as f of t, comma g of t, defined by these equations, is a parametric curve. We call these equations parametric equations. These are parametric equations for the curve. Notice how I'm not saying these are the parametric equations. We'll see that parametric equations are not unique for a given curve. So we could say these equations are a parametric equation set. The variable t is called the parameter. And its domain, I, is the parameter interval. If I is a closed interval, say the interval is a less than or equal to t less than or equal to b, then the initial point of the curve is f of a comma g of a. So it is the x and y value that correspond to letting t equal a. And the terminal point is f of b comma g of b. All right, so let's see an example of this. So example, sketch the curve defined by the parametric equations x equals t squared and y equals t minus 1, where t ranges from negative infinity to positive infinity. So the coordinate pairs are t squared comma t minus 1. So x is t squared, y is t minus 1. The way we're going to do this is we're just going to do a table of values and then plot those table of values. So we have t, x, y. And then we'll come over here and we'll plot them as we go. 2, 4, 6, 8, 10. 1, 2, 3, 4. So when t equals negative 3, then x is t squared, so that's 9. And y is t minus 1, so that would be negative 4. So when t equals negative 3, we are at 9 comma negative 4, so we're down here. T equals negative 3. When t is negative 2, we're at 4 comma negative 3. So that'd be 4 comma negative 3. When t is negative 1, we're at 1 comma negative 2. And when t equals 0, we're at 0 comma negative 1. When t is 1, we're at 1 comma 0. And we're at 2, we're at 4 comma 1. And when we are at 3, we're at 9 comma 2. Connect the dots. And then whenever you draw a parametric curve, you should always indicate the direction. So we are going in this direction. So this looks like a parabola rotated 90 degrees. So this probably has equation x equal y squared-ish. And we'll see how we can convert a parametric equation to a normal Cartesian equation in a little bit. And by that I mean right here. So example, eliminate the parameter in the previous example. Solution. We're going to use substitution to eliminate t. So we have y equals t minus 1. Solve this for t, and you get 1 plus y equals t. Plug this into x, so we know that x equals t squared. So then x equals 1 plus y quantity squared. And that agrees with what we established above. We said x is going to be y squared-ish, and here we have x equals y plus 1 squared. And for those interested, if you solve this for y, you get y equals plus or minus root x minus 1. But leaving it as x equals is perfectly fine. Okay. Next example, let's do something similar. Let's graph x equals 3 cosine t and y equals 3 sine t. In the previous example, we let t be anything we want. Here we're going to restrict ourselves to t being between 0 and 2 pi. So here we have a closed interval, parameter interval. So we will have an initial point and a terminal point. Again, we do a table of values, t, x, y. And I'm going to pick strategic values of t that I can actually get values for. So we'll do 0, pi over 4, pi over 2, pi, 3 pi over 2, and 2 pi. When t is 0, 3 cosine t is also 0. That is wrong. 3 cosine t is 3, and 3 sine t is 0. So we get 3 comma 0. When t is pi over 4, both cosine and sine are root 2 over 2. Multiply both of those by 3 to get 3 root 2 and 3 root 2. Kind of hard to graph, but that's somewhere like here-ish. When t is pi over 2, cosine is 0, sine is 1, so we get 0 comma 3. When t is pi, we get negative 3 comma 0. When t is 3 pi over 2, we get 0 comma negative 3. And when t is 2 pi, we are back to 3 comma 0. So t equals 0 is the initial point, and t equals 2 pi is the terminal point, and it just so happens that these are the same point. This path is closed. Connect the dots, and we get a perfectly drawn by hand circle. This is a parametric equation, so draw your direction. This is why I chose pi over 4, was to see the direction of the curve. And there you go. If we wanted to write this as a standard, if we wanted to eliminate the parameter, we would use the fact that 3, I'm in blue, if we square both x and y, and then add them together, so this is x squared plus y squared, then we get 9 times cosine squared plus sine squared. And we know cosine squared plus sine squared is just 1. So we would get x squared plus y squared equals 9. And we know that this is a circle of radius 3. So we knew, so that agrees with our curve that we drew. However, x squared plus y squared equals 9 doesn't have a direction. So when you eliminate the parameter, you're eliminating the direction that the curve is traveling in. Okay, example. We've gone in one direction. I've given you parametric equations, and I've asked you to find or eliminate the parameter. So now let's see an example of the other direction. I give you something without a parameter, and I want you to parameterize it. So give a parametrization of f of x equals x squared. So we have one obvious parametrization. It'll be obvious after I say it. And this obvious parametrization is known as the natural parameterization. Oh no, I made it fit. That natural parameterization is to just let x equal t. If x equals t, then y equals t squared. This is a valid parameterization. Let's go ahead and graph this. If you were to graph this, you would see that you get obviously a parabola, because that's f of x equals x squared. But figuring out the direction, when t equals 0, you're at 0, 0. When t equals 1, you're at 1, 1. So you're here. So go from 0 to 1, you're going this direction. So we know that is the direction of the curve. So is this the only parameterization? The answer is no. We could also do x equals negative t and y equals t squared. This is also a valid parameterization for this curve. And if we were to graph this one, it's also going to be a parabola, because if you eliminate the parameter, you still get a parabola. But now at t equals 0, we're at 0, 0. At t equals 1, we're now at negative 1, 1. So now we're here. So we know that the direction has reversed. So parameterizations are not unique. They might only be off by a direction, and to do that, you just replace t with negative t. But parameterizations are not unique. Okay, next example, let's do one that's not, let's find a non-natural parameterization. So find a parameterization for the line through the point a comma b with slope m. So really, we're finding a parameterization for a standard line. So to do this, the equation of a line is y minus b equals m times x minus a. We have a lot of different options here for what we could do. We want a non-natural, so we're not just going to let x equal t. Instead, what we're going to do is we're going to pick something else for t to equal. And we're going to just group this x minus a together and make that equal to t. So let t equal x minus a. And then solve this for x, and you get x equals t plus a. And y equals mt plus b. If this is t, then you have y minus b equals mt. Just bring the b over. Thus, our parameterization is x comma y equals t plus a and mt plus b for negative infinity to t to infinity. So there exist non-natural parameterizations, and we could have gone further. We let t equal x minus a, but we could have let t equal m times x minus a, and then y would be t plus b instead of having that m there, and x would be a little bit different, all of which are valid. So there are a lot of different parameterizations for each curve. Last example. Sketch the path traced by x equals t plus 1 over t and y equals t minus 1 over t for t greater than 0. So I'm going to let you guys work on this. Try this, and then when you're done, come back and see if you got the right answer. So to do this, we draw a table of values. We can't choose negative values, so we'll get close to 1, and then we'll get, close to 0, and then we'll get large. So we'll look at 0.1, 0.2, 0.5, 1, 2, 4, and 10. 0.1 is 1/10, so plugging that into x, you get 0.1 plus 1 over 1/10, which is 10, so you get 10.1. Y, on the other hand, is negative 9.9. For t equals 0.2, we have 5.2 and negative 4.8. For t equals 1/2, we have 2.5 and negative 1.5. For t equals 1, we have 2 and 0. For t equals 2, we have 2.5 and 1.5. For t equals 4, we have 4.25 and 3.75. And for t equals 10, we have 10.1 and 9.9. Drawing this, you get a curve that looks something like this. Drawn pretty horribly. So this would be t equals 1, this would be t equals 2, and so on. So this is our direction. But note, this is not a parabola. This has a slanted asymptote there, an oblique asymptote there. Flashback to geometry. This is a hyperbola. So if we wanted to solve this or eliminate the parameter, the first thing, let me rewrite it so I can see it. How would we do this? You can't really solve these easily for t. So instead of solving these for t and doing the substitution method, we would try to be sneaky and maybe like add or subtract the two x and y to try to eliminate something. So if we do x plus y, then this is nice because the 1 over t's will cancel. And you would just get 2t. If we subtracted the 2, then it's also nice because the t's will cancel. And we'll just be left with 1 over t's. So that would be 2 over t. If we multiply these, we would have x plus y times x minus y is 2t times 2 over t. The t's cancel, and we just get 4. So we have eliminated the variable. What is the left-hand side, though? This is a special product. This is a difference of squares. So we get x squared minus y squared equals 4, which is the equation of a hyperbola.